Okay, so 5.3 in your text is concavity and points of inflection. We're going to talk about that as clues to sketching the curve. We talked about intervals of increase and decrease. We know where the maximum minimums are. We know where horizontal and vertical asymptotes are now. This is the next piece. So just by way of a little introduction here, concavity is our first, the first word in this title. So what is concavity? It has nothing to do with the dentist, thankfully. This shouldn't be painful, other than the typical kind of math pain that you get when you do your homework. But concavity basically means that you've heard the word concave before, right? And that is the root to this word, concave. Okay? I have a couple examples down here. So from point A to point B, all right, there are a number of different ways to get there. This dotted line would be the direct path between A and B. Now, most functions are not composed strictly of straight lines. They have curvatures in them. And so where the graph would emulate something like this curve right here, okay, this section between A and B here, this would have a concavity, and we would call this concave. You know what the word is? Concave. We've used it before in algebra, in pre-calculus, for a parabola that sort of exhibits this sort of behavior. It looks like that, doesn't it? So what was the concavity of this parabola in pre-calculus? Concave upward, yes, and we'll just say concave up. Right. That's very good. This is concave up. Now, if the graph between the points A and B exhibited some sort of behavior like this, where the concavity is obviously different, we would call this concave what, do you think? Yes, concave down. And if we think about a parabola, we said that a parabola's concavity was concave down. If you remember, we did this. See, D is concave down because it opens downward. And so if you examine a piece of this parabola, it sort of looks kind of the same as this piece. So that's the first thing in understanding concavity. Okay. Now, obviously, if we have a graph that looks like this, well, what do we have there? Is that looks like there's two specific pieces there, and that's exactly right. And we will talk about that next here. But you're going to have a section where the concavity is uniform, and another section where it's the same as well. Okay? So the first step is understanding concavity. Questions about that? Okay. If it's a straight line, then it doesn't have concavity. We'll talk about that. That'll come up a little bit later. Now, points of inflection. I want to talk about points of inflection when we take a look at this next graph here. This is just kind of a typical sort of section of a sine graph, maybe something like that. But what I want to outline here is that the concavity, as I just mentioned, there seems to be several sections to this graph that's showing here. And it's true that from here, this point, A, to a point somewhere between A and this point, there is a switch that happens. So maybe right about there. And you could maybe see that this section of the graph is concave what? Up. And this section of the graph is concave down. Okay, you see that? It's uniform. And this point right here, where concavity changes on a graph, is called the point of inflection. So this is the point of inflection. Now, if you have a lot of inflection in your voice, you sort of, your tone and your volume, it varies quite a bit. There's a lot of inflection in your voice, right? So we're talking about sort of like a swelling or a changing. So if I kind of think about that. If you're, in the play or whatever, and you have a speaking part, right? You don't talk like this all the time. Hello, my name is, I'm so glad to be, unless you're a robot, this is not the way people talk, right? There's a lot of inflection. And so that sort of inflection is where everything changes a little bit. So think about it that way. So here we have a definite change in section. Now, do we have another point of inflection on this half here? Do we have another one? Yeah, probably pretty plain for you to see now that there's another point of inflection right about here. So this is concave down here as well. and this is concave up. Now the interesting thing is, actually, I don't know if you maybe would question this or not, but the use of color here maybe shows you, but this whole section from here to here is all concave down. I just put that point up at the maximum just to kind of show you the two opposing parts. But really, if we take a look at this all together, this is concave down all the way from here, B, to C. Everyone see that? Okay. So we actually have three sections here. In this section, A to B, or we could say over this interval, A to B is concave up. B to C, all right, B to C is concave down, and so on. And then C to D is also up. So everyone see that? Okay. Questions? Okay. So graphically, we can kind of see concave up, concave down. What does that actually mean for us? Well, I want to show you that what concave up and concave actually can be described as. Okay? And this will help you in connecting the graph with the math, or the graph with the calculus here. So concave up. So on this interval, where the graph is concave up, another way to think of it is the derivative, or the instantaneous rate of change, or the slope of the tangent line is always increasing as x increases. So that's a little bit different way to look at that. Now that we know what a derivative means, we can describe this in terms of the derivative. And I'm just going to zip back here a page just to leave that up a little bit there, the first one up. If I can. No, I can't. Okay. So I'll come back to that in a second. But if you look at this concave up section, the derivative here, or the slope of the tangent, would be about there. As x increases, the slope of the tangent also increases. You see that? It gets larger and larger and larger. You see that? The slope is getting larger. And over here, now this is a bit different. This is a little harder to see, but the slope here of the tangent line, there, versus here, sorry about the straightness of my lines, versus here, this right here is a very large negative slope. This is a not as large negative slope. This is a not as large negative slope. So you got maybe, let's quantify this by saying this is like a negative 10 for a slope maybe. This next one was maybe like a negative 7, and this one is like a negative 2. So you see that? How this actually is increasing. The value of the slope of the tangent is increasing, even though they're negative. They are getting larger. That's why this is also concave up. Okay, everybody see that? Conversely, on an interval where the graph is concave down, the derivative is always decreasing. Or the slope of the tangent line is always getting smaller as x increases. So as we move from left to right across the independent, or the horizontal axis, the slope of the tangent line is actually getting less and less. And if I can just kind of go back up here, sorry, I know you might not have it all written down yet, I will come back, I promise. But if we go back to this diagram here, you see how this slope here is coming to 0. So we might have a positive slope. Let's say this is 3, then this is 2, this is 0. So you see that's decreasing. Maybe 3, maybe 2, maybe 0 at the top. And then we're going into the negative territory, negative 2, and then negative 5, and so on. So it's decreasing. Okay. Another way to look at this that I noticed I think there was a notice in this textbook. Another way to think about it is on concave up intervals, when you draw the tangent line, that tangent line is always below the actual graph. So that's kind of neat. See how they're always underneath here. And on a concave down, the tangents are always drawn above the actual graph. So that may help you. Okay, you can look at it that way. Okay, so what does this mean? I want to talk a little bit about, we're talking about concavity, and here's this again if you didn't get all this down. What does the derivative is increasing mean? Let's just take this phrase for example, okay? Because we talked about that, right? As the derivative increases. Okay, what does that actually mean? Well, we looked on the graph and we saw that the actual slopes of the tangent lines are getting larger. Now, let's think about that in other terms. What does a derivative mean in other contexts? A derivative is also a what? Slope of a tangent, but also a, okay, velocity, right? Which is a rate of change of position versus time. Very good. So if a derivative is velocity on a graph where you have, position versus time, then what we're saying is that this rate of change is changing itself, right? Or the example you said was velocity, okay? So we see that the velocity or the rate of change is increasing. Does anyone remember what that is? If your velocity is changing, what is that called? Acceleration, right? And those of you that are in physics, you would know that too. So the change in velocity is acceleration. So what we have is this equals a positive, I'll say velocity because that's the example we're talking about here. So a positive, no, sorry, I made a mistake there. Positive change in the velocity, which we'll just say acceleration. Okay, 2 C's, 1 L. So a positive, I was going to write a positive change in velocity, but we'll just say positive acceleration, which the first derivative in that context is velocity. The acceleration, do you remember what the acceleration is? Yeah, second derivative. So if we have a positive acceleration, that's the same as saying, hey, where the second derivative is positive, that's where we are concave up, right? So that page kind of looks like some of your answers on your quizzes, sorry, but I'll make some sense about this. Okay, we'll summarize that. So the second derivative is what we're going to be using now to determine the intervals of concavity. We're going to use the second derivative because, summary of that last page there, when the second derivative is positive, that is, the first derivative is increasing, we are concave up. So the rate of change of the first derivative is increasing. That is a positive second derivative. Okay? And then, of course, where the second derivative is negative, that represents a decreasing of the first derivative, a constant decreasing. All right? Well, it actually doesn't have to be a constant decreasing, but it is a steady decreasing. And that is concave down. Okay? Okay, so in this example right here, okay, now just take a moment just to look at this. Don't be writing this down, just follow me. It's already done for us. Let's take a look at this. If I ask you, where is the function concave up? What I'm asking is, where is the second derivative positive? That's really what I'm asking, okay? A concave up is wherever the second derivative is positive, or the x values that cause the second derivative to be greater than 0. That's what I'm looking for. So how do we get there? Well, if I give you a function like this right here, you need to find the second derivative. So you find the first derivative right here. Power rule, right? Bring that down. This is baby stuff now, right? Okay. 6x plus 4.